Hey there, this is help to get you started on the Sled Wars Gizmo. In terms of the due date, you'll be working on it today and Monday. So we are looking at end of class, and to be honest, when I'm actually going to enter them is going to be 3 o'clock Monday. So drop it off anytime. As always, we do the first page together. So the number 1 says, a firefighter is trying to break through a door. Is he more likely to break through if he runs at the door very slowly, or if he runs at the door very fast? And explain your answer. Okay, a lot of this is just super simple common sense. If you're going to try to break through something, we need some momentum. All right, so we want to go fast. The reason for that is going to increase your momentum, because remember, momentum is the mass and then your change in velocity. So can't do much about your mass, but if we can have a big velocity that we bring down to 0, we have more momentum, bigger impulse on the door. Number 2, 2 firefighters are trying to break through a door. One is heavy, the other is light. Okay, so we've got a big mass here, little mass here. If they run at the same speed, which one is more likely to break through? If you need somebody to save you, myself or Mr. Butchkowski, you better pick Butch if you need a door knocked down, all right? Because that big mass, okay, so we would say the heavy firefighter, because an increased mass means increased change in momentum, bigger impulse on the door. All right, so we've got to start talking in terms of impulse and changes of momentum. Okay. You're going to load up the Sled Wars Gizmo. This is the one with the Yeti sledding down the hill, so it's more fun to look at, if anything, of the other gizmos. And it's pretty straightforward. We're going to deal a lot with energy here, which is this unit and the next unit. Yesterday, in that car crash physics, you at least heard the words kinetic potential energy. We're going to play around with those a little bit now in this one. So it says the ability to crash through doors and cause other changes depends on an object's energy. With the Sled Wars Gizmo, you'll explore the factors that affect the energy of a sled. So the Gizmo shows a Yeti named Bert riding his sled down a steep hill. Bert plays a game where he tries to wreck as many snowmen as he can. I can't show you the Gizmo screen and this all at once, so you just need to follow along on your Chromebook. And you're going to take that red slider that says red sled mass, and we're going to, by default, we might be leaving this one. Yeah, we're going to leave that one at 100 kilograms. Notice where he's at here. You can change where he's at by actually grabbing onto him. So if you take your cursor and put your hand on the Yeti, you can drag him up and down that hill. All right. So it says set the snowmen to 5. That's the blue slider on the right. So you should have 5 little snowmen. He stays at 25. He stays at 100 kilograms. You hit play. And then you get some good sound effects if you have sound effects on. Now, he destroyed one snowman totally and then took the head off the next one. Obviously, this is very violent. This line didn't copy. We aren't going to say like 1 1/3. Underneath in the bottom right-hand side, you see collision result. That is what you want to look at. So snowmen destroyed is 1.23. All right, 1.23. You're going to click reset, which is that little curly Q arrow, and it says set the red sled mass to 200 kilograms. So now the slider goes to 200, and we're going to hit play. And now you're going to see how many he destroys this time. All right, we're not going to say, 2 2/3. We actually look down and get the exact number. Is 2.45 snowmen. 2.45 underneath the collision result. You click reset again. We're going to drag the sled to the top, so the starting height is 50. So you put your cursor again on the little Yeti guy, drag him towards the top, and it gives you the height at 50. It didn't say to do anything with the mass, so we don't change it. Anything with the snowmen, we hit play. And do we have total destruction? Oh, so close. That looks destroyed to me, but they're going to say 4.9 snowmen. And question is, why do we think this is so? So why are we getting more destruction the further he is up the hill and the more mass he has? All right, so think about that. If we have more mass and a bigger velocity, and a greater velocity, because the longer he's sliding down the hill, the longer gravity has to accelerate him down the hill. Okay, that's going to give us a greater change in momentum when he hits those snowmen, which means a greater impulse on the snowmen. Remember, impulse is that force multiplied by the time at which it acts. All right, so that's the first page. And I'll give you a second to see if I'm going too fast, too slow. You could always pause me. All right, back page. Click reset. Okay, just remember to read these answers, so we're going to reset it. We need one sled. It defaults to one sled still at the top. Red sled mass, take it back down to 100. Set the number of snowmen to 0. No snowmen. Check that the height of the sled is 50. So we're going to leave him towards the top. We know speed is how fast an object is moving, so it's distance per unit time. The units in this gizmo are meters per second. So we're going to start with a sled at 50. Click play. Observe the red sled speed speedometer. What happens to its speed as it moves down the hill? Hopefully you saw that it increased. Now acceleration, on the other hand, is a change in speed or direction. Remember, or it could also be both. So in what two ways does the sled accelerate as it descends? So as it comes down the hill? Well, it gains speed, but also think about the direction component. Because here comes the little Yeti guy. So he's moving here, this direction, then this direction, then that direction. His direction also changes. So he increases speed, and there's a change in direction. We have to get used to that triangle, meaning change in. Reset it again. This time, focus on the speed of the sled after it reaches the bottom of the hill. Click play. What do you notice? So we leave everything the same, except now we're going to watch him when he reaches the bottom. So it looks like he's going 31.3, and then he leaves us. So at that point, he stays at a constant 31.3 meters per second, and he's going the same direction until he leaves our screen. We don't know where he went, right? Because he just keeps on going to the right. So 31.3 and same direction, that is telling us then that he is not accelerating, because that is a constant velocity. Same speed, same direction means constant velocity. Okay, I'm going to leave you here on this part. You can figure it out. Red sled mass 10 kilograms. Just remember to read the direction. I'm going to flip. So this is just where I'm previewing and helping. If you would, turn to B real quick. One of the things that messes people up, and I changed the wording to see if this helps. At one point you need the Yeti at 25. At one point you need it at 0. This one is anywhere between the top and bottom. It could be 12. It could be 13. It could be 14. Whatever. Just drag the Yeti and start him somewhere in between 0 and 25 and write that number down. So that means these numbers could be different for every person in this class. But total energy is what is going to be important. If we total something up, that means we add. So your potential and kinetic energy add together for total energy. And so what you have to make sure you see, let me see where this is at. Somewhere. You might have already checked it, but you need to have show energy checked in the top right-hand corner. It'll show you the potential and the kinetic, and those should always total to the same number. Okay, so let's just do this. What do you notice about total energy? They should work out to be the same. We're going to keep going through here. That should be pretty self-explanatory. We're going to flip. We'll just keep following directions. Extension 1 and 2. We will do it together. Okay, we will do this together. Potential energy. You don't know this yet, but the way that you figure it out is mass times gravity times height. And we usually use 10 for Earth's gravity, we just round it, but they want to use 9.8 for this one. So what we do is to calculate the potential energy of a 20 kilogram sled at 40 meters, that's going to be our height. So I'm going to leave a little gap here for gravity. So 40 meters above the ground, and gravity is 9.8. All you do is multiply those together. So I'll leave that to you. Okay, so I'll plug those into a calculator. 20 multiplied by 9.8 multiplied by 40. Now that's going to be at the top of the hill at rest. As he comes down the hill, that potential turns to kinetic. That's the moving energy. And the formula for kinetic energy is 1/2 of the mass, which is 20 kilograms. And then, instead of using the 40 meters, we don't care as much about that. We know from running the simulation, at that point, he's going 28 meters per second once he's going to the bottom of the hill. That gets squared. All right? I'm not sure how comfortable we are with squaring things, but it's something we've got to get comfortable with. I'm going to help you do this one. 28 squared is an order of operations thing. When you see an exponent, you have to do that first. 28, you're going to use the caret button. Okay, that's the caret button. I used to have people use the x squared. Miss Narker yelled at me, in her nice way, of course, because there's not always a base 10, all right, when you guys work with exponents in her class. So we're always going to use the caret 2. That means 28 is squared. So that's our first step. Now I always hit enter. After that, we multiply it by 20. Hit enter again. And then we take half of that. You could either multiply it by 0.5 or divide this answer by 2. Okay, I'm just going to multiply it by 0.5 because that's half. And we get an answer of 7,840 joules. 7,840 joules. The answer here should make you wonder if you were correct. You probably are. So if you're like, why is that answer something related to that answer? You're good. All right, that's how you know you did it correctly. Activity C, 2 sleds. We've got 2 Yetis now. And make sure you read the potential energy of each sled. So there'll be show energies that you have to look at. Down here, you're just looking at a speedometer. Remember, our momentum is going to be mass multiplied by its velocity for the red, momentum for the blue, mass multiplied by the velocity for the blue. We go to the back. To get the speeds, you are looking at the speedometer. And here's the most important part. Probably going to get the most questions right here. If you let them hit, your speed is always 0. Don't let them hit. Click pause just before the sleds collide. Just before. You're going to record the speed. You have to calculate momentum. Okay, that one you have to do. Mass times the velocity. Mass times the velocity. The winning sled, thinking back to car crash physics video, give a more massive car, that often is the one that pushes the other one back. So whichever one has the most momentum. So you're going to have blue or red here. And what they want you to do is end up circling those. All right, but what I'm most concerned about is you write blue or red, blue or red, blue or red. Here's where they tell you to circle it. What you should always see, the winning sled had more starting momentum. This one, you're going to click and have the select that the sleds bounce. All right, this is an elastic collision. And then click reset without changing any of the masses or heights. Okay, so we're going to leave it as we were here. Okay, we'll still have that. Record the potential and kinetic energy of each sled. Find the total energy before the collision and then after the collision. So you calculate it before they hit and then pause it after they hit. And these two numbers should be the same. that number and that number, those should match. If they don't, we've done something wrong. Okay, and that, if those don't match, then the answer we're going to do together right now is false. Okay, and it shouldn't be false. Energy is conserved, because what conserved means in physics is that the total energy stays constant. It's not like, and we'll talk more about this next week, it's not like conserve your money means to save money, build up more money. Conserved here means just keep it the same. Okay, so it's not like conserve water, take shorter showers. Okay, that's not what it means here. It means that the total energy before the collision should be the same as the total energy after the collision. All right, get started.